Okay, let's start our class. The plan for the following lesson is like this. Let's first talk about RL. Then the teaching assistant will announce the assignment. Okay, regarding the last part of RL, we mentioned that we want to learn an actor. This time, we want to learn another thing. This thing is called critic. I will first explain what the critic is. Then I will talk about the help of the critic to the learned actor. Okay, let's see what the critic is. What is the critic? The job of a critic is to evaluate the quality of an actor. You already have an actor, and its parameter is called theta. Then the critic's job is to evaluate the reward this actor might get after seeing a certain observation or a certain game screen. There are many different variants of the critic. Some critics just consider the game screen to judge. Some critics consider a certain game screen and a certain action that the actor took. It decides the rewards you will get, depending on both conditions. Maybe it is still a bit abstract, so let's be more specific. We give an example, and it will be used later. You can use it in your homework. This critic is called value function. We use uppercase V theta of S to represent this value function. What is its input? Its input is S, which is the current state of the game. For example, the screen of the game. Please pay special attention to the V. It has a superscript theta. What does this superscript theta mean? It means that this V observes the actor theta. What about the actor it observes? Its parameter is theta. What about this V? V theta is a function. Its input is S. The output is a scalar. Here we use V theta of S to represent this scalar. What about this scalar? What is the meaning of this value? The meaning of this value is the discounted cumulated reward it gets if this actor theta, the one in the superscript, sees observation S, sees the inputted game screen of S. Do you remember what discounted cumulated reward is? Do you remember what we said before? When evaluating the quality of a certain action, you can't just look at the reward after the action is executed. You have to add the reward after executing that action, and all the following rewards, to get a cumulated reward called G. Then, you will be able to evaluate how well the execution of a certain action is in a certain state. But we also said, you add all the R from the execution of a certain action to the end of the game. All the R are directly added together, which is not a good idea. You should multiply a discounted factor called gamma, meaning that the reward you got farther from the time of this certain action has less relation to the action. So it should be multiplied by a discounted factor called gamma. Then we get G prime. What is this G prime? It is a discounted cumulated reward. We use the value function to estimate how much discounted cumulated reward a certain actor will get if it has seen a certain game screen. Of course, to get the discounted cumulated reward, you can play the game till the end. You already have actor theta. Suppose it sees this state S. Then how much G prime will it get in the end? You'll know it after playing this game. But the purpose of this value function is to guess the future. Guess before you see it. Even the game is not over yet. After seeing S, it has to predict how well the actor can achieve. This is what value function does. For example, suppose you give the value function this game screen. It should directly predict that you should get a very high cumulated reward after seeing this game screen. Why is that? Because in this game, there are still many aliens. Suppose your actor is very powerful, and it is a good actor, which can kill aliens and get a lot of rewards. This game screen is already at the end of the game, the final round of the game. The game is almost over. There are few aliens left. There are only little rewards left. Then these values would be known after you play the whole game. But what the value function wants to do is to guess the result before the game is over. It wants to guess how much discounted cumulated reward you would get. There is one thing that needs to be emphasized. This value function has a superscript theta. This value function is related to the actor with the same observation, the same game screen, and a different actor. It should get a different discounted cumulated reward. In the last example, I said that suppose we have a good actor. After seeing this game screen, we will have a high value. And seeing this game screen, we will have a low value. But suppose your actor is weak. Aliens can easily kill it. Then maybe after seeing this picture, the value is low, because there are a lot of aliens. Your actor could be killed in few moves. It won't get any reward. In this screen, this weak actor may also get a low V. As a result, the output of the value function is related to the actor. Okay, so this is critic. Before telling how the critic is used in reinforcement learning, let's talk about how to train the critic. There are two commonly used training methods. The first method is the Monte Carlo-based method. It is abbreviated as MC here. Okay, then how to train this value function? How to train the critic v theta? If you use the MC method, intuitively, you can just do as following. You just let the actor interact with the environment. Let it interact many rounds. After the actor interacts with the environment, plays the game, we will get some game records. You will find that, if the actor sees SA, the coming cumulated reward will be GA prime. You have played a lot of games and finished them. We know that. When the agent sees observation SA, the cumulated reward will be GA prime. I omitted discounted here. Anyway, you know what I mean. Then, your value function will get training data. This training data tells the actor that, if it sees SA, and its output, v theta of SA, should be as close to GA prime as possible. Sample and get another observation. Another game screen. You can get the cumulated reward GB prime. After finishing the game, input SB into the value function. You will get v theta of SB. The v theta of SB should be as close to GB prime as possible. The approach is very intuitive. Observing the actor, you will get the cumulated reward. After sampling, you will get training data. Train value function using these training data directly. Monte Carlo is a very intuitive approach. Next, let's look at another less intuitive approach. This approach is called the temporal difference approach. The abbreviation is TD. In the temporal difference approach, you can get the training data for the value function without playing the entire game. For an observation ST, the actor takes action AT, gets the reward RT, and the observation ST plus 1. Seeing such a piece of data can train V pi of S. Seeing tuple ST, AT, RT, ST plus 1 can be used to update the parameters of V pi of S. If you can update the parameters of V pi of S using a piece of data, what are the benefits? In Monte Carlo, you have to play the entire game to get a piece of training data. Some games are very long. Some games may not end at all. It always goes on forever. It never ends. It is very unsuitable for you to use MC for games like this. In these cases, you can use the TD approach. How can we train V pi of S? Only when we see such information. Here is an example. Let's look at the relationship between V theta of ST and V theta of ST plus 1. What is V theta of ST? V theta of ST is the cumulated reward after seeing ST. V theta of ST is RT plus gamma RT plus 1 plus gamma square RT plus 2 and so on. Then V theta of ST plus 1 is RT plus 1 plus gamma RT plus 2 and so on. We find that there is a relationship between V theta of ST and V theta of ST plus 1. What kind of relationship is it? V theta of ST is equal to V theta of ST plus 1 multiplied by gamma plus RT. Multiply each item by gamma and add RT. Will become V theta of ST. There is a relationship between V theta of ST and V theta of ST plus 1. Now, after we have such a piece of data, we can use it to train our value function, hoping that value the function can satisfy the formula we wrote here. What does it mean? Suppose we have a piece of data. We input ST into the value function to get V theta of ST. Input ST plus 1 into the value function to get V theta of ST plus 1. Although we don't know what the value of V theta of ST and V theta of ST plus 1. We know the difference of subtracting one from another. According to the equation as mentioned earlier, we multiply V theta of ST plus 1 by gamma and subtract from V theta of ST. This value, V theta of ST minus V theta of ST plus 1 multiplied by gamma, should be as close to RT as possible. Here's RT, which has been collected in the dataset. We also know the relationship between v theta of st and v theta of st plus 1. So we know that v theta of st minus v theta of st plus 1 multiplied by gamma should be as close to RT as possible. Input st and st plus 1 into v theta and subtract one from another. Then, the value should be as close to RT as possible. This is the TD method. Okay, so we introduced two methods to train the value function. Which is the critic? One is MC, and the other is TD. Actually, if you use these two methods, which are MC and TD, to calculate the value function of the same data, then the value functions you calculated are likely to be different. Let me give you an example, which looks like this. We observe an actor. The actor had interacted with the environment and played the game 8 times. For simplicity, we assume that the game is so simple that it can be finished in 1 or 2 rounds. So when the actor played the game for the first time, SA is observed, and the reward is 0. Next, SB is observed, and the reward is also 0. Game over. Subsequently, in the following 6 games, only SB is observed, and all end up with the reward of 1. In the last game, however, SB is observed, but ends up with the reward of 0. Here, we ignore actor, and also assume gamma is equal to 1, for simplicity, which means that there is no discount. Okay, so how much is v theta of SB? We know that v theta of SB represents the expectation of the reward. When observing SB, in this example, SB is observed 8 times in total. I saw SB every time I play. Then, what is the expectation of rewards you get after observing SB? We got 1.6 times, and got 0 points twice. So the average is 0.75 points. V theta of SB should be 0.75. There's no controversy at all. What should the V theta of SA be? After seeing SA, how much do you think the reward should be next? Based on these 8 training data? How much reward should the SA be next? Okay, I give you 10 seconds to write your answer on the message board, or type your answer on the message zone. I will use this free time to answer questions from classmates. Do we have any question? Okay, if you have any questions, you could send them to the chat room. Next, I will give everyone some time to think. How much do you think the V theta of SA, based on the 8 training data we have seen, should be? You could put your answer in the chat room, and I will check if this chat room can be used. Yes, it can. Okay, I have seen a lot of answers. Nearly everyone said it is 0. Almost everyone said it is 0. Do we have other answers? Okay, there are almost no other answers. Everyone said it is 0. Okay, the majority of students said it is 0. Is 0 a correct answer? It is both right and wrong. Actually, there is another possible answer, which is 0.75. I don't see anyone answering 0.75. I will explain it later. Why is it possible to calculate 0.75 out? But, at the same time, 0 is also a reasonable answer. Why do you think it should be 0? 0 is obtained by Monte Carlo's ideas. Why is it 0? Because we have seen SA only once. How much reward will it be after seeing SA? It is 0. After seeing SA, the reward is 0. After seeing SB, the reward is still 0. So, the cumulated reward is 0. So, if you look at it from the perspective of Monte Carlo, after seeing SA, what the calculated G should be is 0. So, V theta of SA should be 0. There's no doubt. Almost all the students choose the correct answer. But, if you use TD, what you calculate might be a different result. How is this? Because, between V theta of SA and V theta of SB, there is a relation. This V theta of SA should be equal to V theta of SB plus reward. That is the reward after seeing SA. Next, it enters SB. Then, this V theta of SA should be equal to V theta of SB plus this reward. The notation here is not so well. This R refers to this R here. So, according to this idea, what is V theta of SB? It's 0.75. What is this R? It's 0. But, V theta of SA should be 0.75, right? According to the idea of TD, V theta of SA should be 0.75. You might ask that, between Monte Carlo and TD, which is right? They both can be right. They just have different assumptions behind them. For Monte Carlo, it looks directly at the data we observe. Since the cumulated reward of SA followed by SB is 0, V theta of SA should also be 0. But, for TD, the assumption behind it is SA has nothing to do with SB. Seeing SB after seeing SA will not affect the reward of SB. These 8 training data give you an illusion, thinking that V theta of SA should be 0. That's just because the number of data you sampled is too small. For SB, the reward is expected to be 0.75. But because of bad luck, the R of SA preceding SB is 0. However, the expected value should be 0.75. You just happen to be out of luck to see that R is 0. And you think SA is 0. But SB, the expected reward after seeing SB should be 0.75. So after seeing SA then sees SB, the expected reward you get should also be 0.75. So from the perspective of TD, how much reward SB will get has nothing to do with SA. So the cumulated reward of SA should be 0.75. But for Monte Carlo, it doesn't think that SA and SB are irrelevant. Maybe SA is an unlucky observation. If you see SA, the reward that SB will get is affected. Maybe after seeing SA, SB will get 0 rewards. They can affect each other. Therefore, SB will be equal to 0 if SA precedes it. Then V theta of SA should be equal to 0. So, in short, there will be subtle differences between calculating with MC and calculating with TD. Let me see if any classmates have questions. Okay, so far, none. TA says, only one classmate answered 1 and all the others answered 0. Okay, so this is MC and TD. This is MC and TD. Now we will see how critic is used to train actors. Remember the last time when we talked about actors? We talk about how to train an actor. You interact the actor with the environment and get some reward. Then you get a bunch of pairs of observation and action. Then you evaluate how good is action A1 at S1 and get a score of A1. We called A1 the cumulative reward. A student asked last week, doesn't cumulative reward need to do normalization? It needs to do normalization. So, we subtract B as normalization. But what should the value of B be? It's hard to say. A reasonable way to set the value of B is to set it to V theta of S. Suppose now you have trained a critic. Based on these training data, you can also train a critic. After you trained a critic, give it a step, and it will generate a score. Then you take this score as B. You treat this score as B. So G1 prime needs to subtract V theta of S1. G2 prime needs to subtract V theta of S2. And so on. Okay, the next question is, why subtracting V is a reasonable choice? Let me explain this on the next slide. Now, we already know how good the SA pair is, which is represented by AT. We define A as G prime minus V theta of ST. Okay, let's take a look at V theta of ST and what it means. What's the meaning of V theta of ST? V theta of ST is the reward we're getting after seeing the scene ST, and it is actually an expected value. The reason it's an expected value is that if we continue playing the game after seeing some scene, the reward we get would be different every time, since the game contains randomness. So, V theta of ST is actually an expected value. Now, the actor might not execute action AT after seeing scene ST. Why is that? Why won't it necessarily execute action AT? Don't forget that the actor itself contains randomness. During training, we even encourage the actors to be random. So, the actor won't necessarily execute the same action when seeing the same scene. The output of the actor is actually a probability distribution. It is a probability distribution in the action space. It also gives each action a score. When we sample actions based on the scores, some actions have a high probability of being sampled, and some have a low probability of being sampled. However, every action sampled does not need to be the same. So, there are many possibilities. After seeing ST, and we get different cumulative rewards, or discounted cumulative rewards, if the discount is involved. For now, we'll omit the matter of discount, since everyone knows what I mean by that. In the slides, the prime symbol was not added, but it's fine as long as you get what I mean by that. Then, we get v theta of ST by averaging these possible results. This is the meaning of v theta of ST. Okay, what is the meaning of GT prime? GT prime is the cumulative reward we'll get after executing AT when seeing the scene ST. So, after we execute AT, we continue playing the game. Down the road, we get a reward, which is GT prime. What does it mean if AT is greater than 0? If AT is greater than 0, it means that GT prime is greater than v theta of ST. At this point, it means that this action is better than the action we sampled randomly. When we get GT prime, we're certain that AT was executed. When we're calculating v theta of ST during ST, we weren't sure which action would be executed. So, when we executed action AT, the reward we got was greater than the reward obtained by randomly executing an action. So, when AT is greater than 0, it means that AT is better than a randomly executed action, indicating AT is a good action. So, we give it an AT greater than 0. On the other hand, what does it mean if AT is less than 0? When AT is less than 0, it means that the reward we get from executing AT is lower than the average reward. The action you took randomly, which was sampled from a probability distribution, resulted in a higher expected value for the cumulative reward than the action AT. If that is the case, AT is a bad action. So it should be negative. This is very intuitive, right? Now you understand why we should subtract v theta of ST from GT prime. But isn't this formula a little bit strange? GT prime is the result of a particular sample. It is the result of executing AT. But v theta of ST is the average over many different paths. Does it make sense to subtract the average from a sample's result? Maybe this sample is, unfortunately, very bad. Shouldn't we subtract average values from average values? This idea leads to the last version we are going to talk about in this class. We get reward RT after executing AT and advance to the next screen stage ST+1. Then, we take account of all the actions you can make after this stage. Take the average of all the cumulative rewards afterward. This is simply v theta of ST+1. You have to play a lot of games to obtain this value, but it doesn't matter. If you've trained a good critic, then you can directly use v theta of ST+1 as the expectation value of the cumulative reward. If you play the game from this stage, adding RT to that number, you obtain the expected reward. Given that you take action AT at stage ST, we already know that the reward is RT for the action AT. Given that we took this action, the expected reward after this is simply v theta of ST+1. So, RT plus v theta of ST+1 equals to the expected reward of taking AT at St. Then, we have to subtract the average reward from it. So we replace GT prime with RT plus v theta of ST+1. And subtract v theta of ST from it. This formula measures how much better it is to take this action AT than to make a completely random action at this stage, which is sampled randomly from the distribution. If RT plus V theta of ST plus 1 is larger, AT is better than average. If RT plus V theta of ST plus 1 is less than V theta of ST, AT is worse than average. It's worse than a random sample from the distribution. This is the well-known and commonly used method called advantage actor-critic. In this method, AT is equal to RT plus V theta of ST plus 1 minus V theta of ST. That's it. Here is a little trick to train an actor-critic model. You might also use this technique in your homework. What is this technique? The actor is a network. The critic is also a network. The input of the actor is a game screen. The output is the score of each action. The input of the critic is a game screen. The output is a number representing the cumulative reward you will get. There are two networks here. Their inputs are the same. So these two networks should have some parameters that can be shared, especially if your input is very complicated. For example, the game screen. The previous layers should all need to be CNN. The CNNs needed to understand the game screen are almost the same. So, the actor and the critic can share the previous layers. When you are doing it today, you will often design your actor-critic like this. The actor and the critic share most of the networks. In the end, output different things. If output actions, it is the actor. If output a scalar, it is the critic. Okay, this is a little trick to train an actor-critic model. What I said today is not all of reinforcement learning. In reinforcement learning, there is another sharp approach, which is to use the critic directly. That is, use the critic to decide what kind of action you want to use. The most well-known of them is Deep Q network, DQN. But we won't talk about DQN in detail here. If you want to know more about DQN, you can refer to the video of past lessons. That DQN has a lot of variations. Here is a very well-known paper called Rainbow. In this paper, the author tried multiple variations of DQN. They tried 7 kinds of variations and then put them together. Since there are 7 kinds of variations, it is called the rainbow. The author called its method Rainbow. I list this paper here for your reference. If you want to know how to do every little trick in the rainbow, you can see the class video. In the past courses, every little trick in Rainbow is detailed. Okay, it comes to an end here. Let's first see if any classmates have problems. Okay, let me answer your classmates' questions. A classmate said that SA is not necessarily followed by SB. If so, what to do? This is a good question. SA is not necessarily followed by SB. So this question, in the case that we saw just, cannot be solved, because the example, with only 8 episodes, SA will be followed by SB. So, we did not observe other possibilities. And we can't deal with this problem. So this tells us that, when doing reinforcement learning, sampling is very important. The final performance of your reinforcement learning is much related to how good is your sampling. So reinforcement learning is a matter of chance. You can experience it in your homework. The result of your sample has a very big impact on your final training result. Next question. Does each V need to correspond to a fixed sequence of environmental occurrences? Hey, let me talk about it first. Wang Dahua is actually a teaching assistant. This is not his real name. The student Wang Dahua is a teaching assistant. Does each V need to correspond to a fixed sequence of environmental occurrences? I'm not quite sure about your problem, but I'll try to answer it. For every V, it will not be fixed. It does not correspond to a fixed order of occurrence of the environment. That is V of S. If your game has randomness, then V actually represents an expectation. What it wants to calculate is, given a certain observation, or a certain game screen, the expectation of the average value of the cumulative reward you'll get. If your game has randomness, V represents the expectation. After you see a certain game screen, what will happen next is not necessarily the same. But we average all the possibilities and take their expected value. This is what V stands for. The S that appears in the back isn't fixed. How to apply the formula to it? Okay, I think I have answered it. The observation that appears later is indeed not fixed. If there are some conditions that you don't observe the observation, then you really can't train. Oh. A classmate asks about taking V as the strength of ordinary people. If surpassing it, it is good. Otherwise, it is bad. Right, it is. V is the average strength. Surpassing V is good. Where do I know this distribution? I think your distribution means the actor's distribution, right? We say the distribution of the action. The action is sampled from a certain distribution. What is this distribution? That distribution is like this. Your actor is like a classifier. Your actor is like a classifier. Then, you throw S into every step. Oh, it's not every step. Every action will have a score. Then, you apply the softmax function on the score and do normalization. It becomes a probability. Then, do sampling based on the probability. This is the meaning of the actor is sampled from a distribution.